Can you see the screen?
Yes, sir.
Yes, sir.
Okay, all right. So the name of the subject is heat and mass transfer. I told you yesterday also. And let us start with some basic introduction part. Thermodynamics. In thermodynamics, we have studied about heat, work, and energy. So first of all, let us see that when two systems are brought into contact through one kind of wall or some kind of wall, energy transfers such as heat and work take place between them. So basically, heat and work are the energy in transition. Actually, you have studied in basic of thermodynamics. Heat, like work, is energy in the process of being transferred. So basically, this is uh, energy in transition, heat transfer as well as the work transfer. So it's written in the next line: energy is what is stored. Okay, so like you have studied about the internal energy that is stored, whereas work and heat are two ways of transferring energy across the boundaries of the system. This is already known to you. The amount of energy transfer as heat can be determined from the energy conservation principle, that is first law of thermodynamics. So we basically utilize first law of thermodynamics and the basic principles of our thermodynamics for calculating the values of energy which is stored within the boundary, or energy which is going across the system boundary, like work transfer and heat transfer. And this we can do only when we consider the system in thermal equilibrium. Okay, if the systems are in thermal equilibrium, then only we can consider that the energy transfer means we can calculate the energy transfer, that is work or heat. Okay, in a finite period when they are connected through a diathermal wall. So basically here they are talking about two systems if they are in contact with each other. Okay, and there is transfer of energy between them. So you can say here we can have a boundary, here we can have a boundary, and the heat transfer or the work transfer is taking place between them. So you remember about thermodynamics, there is a system, there is surrounding. So if we consider one this is the one system, this is the second system. So basically the heat transfer and the work transfer exists between two systems when they are in contact with each other. Okay, so this is you can say is thermodynamics concepts. Okay, now what is temperature? Temperature is a property of matter which two bodies in equilibrium have in common. So it is basically the zeroth law of thermodynamics. You know from the zeroth law of thermodynamics that two bodies when they are in contact with each other, their temperature will have a common value or the same value. So temperature is constant for both the bodies. And we use the objectives hot and cold to describe high and low values of the temperature. This is very basic. Energy transfer as heat will take place from the body with the higher temperature to that with the lower temperature if they two are permitted to interact through a diathermal wall. Okay, so this is second law of thermodynamics. You know the from the Clausius statement that heat always flows from high temperature to low temperature. So this is nothing difficult. The third point is the transfer and conversion of energy from one form to another is basic to all heat transfer processes, and hence they are governed by first as well as second law of thermodynamics. So basically these are simple things which you have studied in thermodynamics and now this is the very important question actually. Okay, what is the difference between the heat transfer and thermodynamics? See, heat transfer we studied in thermodynamics also, and now we are studying going to study this as a separate subject. Okay, so what is the difference in the heat transfer which now we are studying as a subject here, and the heat transfer which we studied in thermodynamics? So this is a very important question for us to answer. So let us see. The major difference between thermodynamics and heat transfer is that in thermodynamics it deals with the relation between heat and other forms of energy, whereas the later is concerned with the analysis of rate of heat transfer. Okay, so you can see it here in thermodynamics, we are interested in the relation between heat and other forms of the energy. That is the one difference. Whereas in heat transfer, we are interested in calculating the rate of heat transfer. Okay, so that is one of the differences. Second difference is in thermodynamics, we consider that the systems are in equilibrium with each other. Okay, system is in, or the process is in equilibrium. The system and the surroundings are in equilibrium. So it cannot be expected to predict quantitatively the rate of change in a process which results from non-equilibrium states. Okay, which is the temperature non-equilibrium, that is gradient, which is a must for the heat transfer to take place. Now this is a very important point when we talk about the subject of heat transfer. See, when in thermodynamics we talk about heat transfer or work transfer, or when we talk about any process, we say that the system is in equilibrium with the surroundings, or it is a quasi-static process. Till it is a quasi-static process, we are able to calculate the value of the heat transfer or the work transfer or the change in internal energy or enthalpy. We talk about the equilibrium. But what will happen if there is no equilibrium? Actually, if you think of any process, the system is never in equilibrium. Okay, if you talk about the heat transfer, for example, if we are considering that the heat transfer is taking place from high temperature to low temperature, this is only possible when there is some temperature gradient. If the temperature gradient will not exist, the heat transfer will not be able to take place. Okay, and the process will never be in equilibrium. The system is never in equilibrium during that heat transfer process. Okay, so in heat transfer we are talking about non-equilibrium states. So that is one of the major difference between heat transfer and heat transfer that you studied in thermodynamics and the heat transfer which we are going to study now. So basically this is equilibrium and it is non-equilibrium. So in heat transfer we are talking about non-equilibrium states. Now let us see further. Heat transfer is commonly associated with fluid dynamics, and it also supplements the laws of thermodynamics by providing additional experimental rules to establish energy transfer rates. So basically, we are interested in when we will be studying heat transfer as a separate subject. So we have to take into consideration fluid dynamics also, and there will be some other experimental rules or additional laws which we have to study to calculate the value of the heat transfer. In thermodynamics we have not used any specific experimental principles or any experimental or any laws through which we have calculated the value of the heat transfer. Okay, it was basically on the energy transfer principle or energy conversion principle that we calculate the values of heat transfer. Now when we talk about heat transfer, this is very important. The knowledge of temperature distribution is essential in heat transfer studies because of the fact that the heat flows from only whenever there is a temperature gradient in the system. For example, if I consider I have a wall here and the temperature here is say 300 degrees Celsius. If the temperature here is 300 degrees Celsius and here also the temperature is 300 degrees Celsius. So do you think that the heat transfer will take place from here to here? No, heat transfer will be zero. No heat will flow. But yes, suppose the temperature here is say 290 degrees Celsius. Here the temperature is say 270 degrees Celsius. And on this surface, suppose the temperature is 200 degrees Celsius. So naturally the heat will flow from high temperature to low temperature in this particular direction. Okay, in a one-dimensional system. I am talking about a one-dimensional system right now. Heat flux is defined as the amount of the heat transfer per unit area per unit time, can be calculated from the physical laws relating to temperature gradient and heat flux. So basically when we say heat flux, you should remember this. See, heat we are denoting by a symbol Q. So if I am using Q, the unit is kilojoules. If I use Q dot, the unit is kilojoule per second. And if I use a symbol Q dot with double dash, double prime, this is basically representing heat flux. and heat flux is basically, I can write it as q double dash is equal to q dot divided by area. So unit for heat flux is watt per meter square. So this is how we calculate the value of the heat flux. If we take this value q dot, then it becomes kilowatts actually. Okay, so this is heat transfer rate, and this is only heat transfer. This part is only heat transfer, and this is heat. This one is the heat transfer rate. So I hope this is clear. And we are saying that temperature gradient is essential for heat transfer to take place. So temperature gradient means, for example, I took this example of the wall. I said the temperature here is 300, and let us say if the temperature here is 270 degrees Celsius, and suppose this is length L. Okay, so I can say, uh, if I say the temperature here is T1, temperature here is T2. So temperature gradient will be equal to T1 minus T2 divided by L. And if I want to write this value in differential form, then I can always write it as dt by dx. Okay, or the direction in which the heat transfer is taking place, that can also be written. Means I can write the temperature gradient as dt by dy also, if the temperature gradient is existing in y direction, or if it is in the radial direction. For example, if it is a cylinder, in that particular case, the temperature gradient can be written as dt by dr. So it is very, very important to know about the temperature gradient if we want to calculate the heat transfer. Now let us think of some applications of the heat transfers in engineering. Now, the study of temperature distribution is, you can say, very, very important in heat transfer, and because of almost universal occurrence in many branches of science and engineering. Okay, as I told you yesterday also, you take the name of any particular branch of engineering, and the heat transfer is a common phenomena there. You talk about mechanical engineering, you are all using machines, and in machines there is generation of heat transfer due to friction between the two surfaces. You talk of the electrical engineering, the cables are there, wires are there, where the heat generation is I square RT. You talk about the electronic devices, heat transfer is there. You talk about computers, heat transfer is there. You think of any phenomena or any branch of engineering, civil engineering, while when you are making the walls with the help of the cement, you know you have to sprinkle the water over the walls so that whatever is the heat generation, or that can be taken care of, because lot of heat is generated when the cement gets dry, and we don't want that that is means that the strength of the wall is good enough. We have to sprinkle the water. You must have seen these all common things at your in nearby, or in your houses, or somewhere else also. Okay, so that means heat transfer is a sort of indispensable subject. You talk of any area, the heat transfer is going to be there, and it's very, very important subject. Now when we talk about the first step in the design, optimal designs of the heat exchangers such as boilers, heaters, refrigerators, and radiators is based on detailed analysis of heat transfer. So I talked about this yesterday also, but here we are talking about the optimal design. You can always design a heat exchanger which may be having a large area. Okay, if the area is large, naturally the heat transfer would be there. But don't you think in that particular case there will be a lot of wastage of money as well as area? Okay, so area is important. For example, if you are living in Delhi, you know the cost of the property is huge, and if you are making use of the large area, that means you are wasting the money actually. Okay, this is essential to determine the feasibility and the cost of undertaking. I just was talking about this only, as well as the size of the equipment required to transfer a specified amount of the heat in a given time. So we would always like that the area is small, whereas the heat transfer is more, because that will save the material cost, that will save the money actually in the terms of material. Okay, if you are using lesser material, the cost will be saved, and if it is higher rate of the heat transfer, That is what is required actually. So cost is actually saved in some way. Modern electric and electronic plants require efficient dissipation of thermal losses. So this is what I am telling you already in electronic equipments. Okay, we have to dissipate the heat. You talk about IC engines also. Okay, you talk about IC engines. There also we need to dissipate the heat. Otherwise, the IC engine will not function properly. A thorough heat transfer analysis is more important for the proper sizing of the fuel elements in nuclear reactors. So in nuclear reactor, you understand the fission reaction is going on, and you have to uh, transfer that heat to some fluid for the generation of the power actually. So if that is not efficient, if the heat is not transferred efficiently, there will be loss of the power generation. Okay, and it is also required to prevent the burnout of the core. Okay, the performance of the aircraft also depends upon the ease with which the structure and the engines can be cooled. The design of the chemical plants is usually done on the basis of heat transfer and analogous mass transfer. So mass transfer is also an important process in that particular case. An accurate heat transfer analysis is necessary in refrigeration and air conditioning applications to calculate heat loads. See, now when you think of, say, a particular room and you want to air condition it, you should know how much heat you want to remove from the room so that accordingly you can choose the air conditioner. You will not choose any window air conditioner or split air conditioner arbitrarily. You should first of all calculate what is the load which is to be removed from the room. Only then you should go for the purchase of a window AC or a split AC. Okay, and to determine the thickness of the insulation to avoid excess in heat gains or losses. So suppose if there is some equipment for which you want to minimize the heat loss. For example, if there is a pipeline which is carrying steam, suppose steam is flowing through this pipeline and it is at high temperature, let us say 540 degrees Celsius. So would you like that its quality should be reduced? No, you would never like that its quality is reduced. So what you will do, you will provide insulation over it. You will provide insulation over it. Okay, so that minimum heat loss is there, and the temperature which you are getting at the exit is near to 540 degrees Celsius. If it goes down to, say, if you are not providing any insulation, the temperature may go to 450 degrees Celsius. So this is a big loss to us, because now the power which will be produced in the power plant will be lesser. Similarly, there can be many other applications, like in solar energy. Proper design of the solar collectors and associated equipment, it also depends upon heat transfer. Okay, then civil engineers must take care of thermal effects in the buildings and other structures. That is what I told you, when the cement is dried or the RCC is poured, the lenter is poured, then also you have to cool the lenter actually. There are only a few examples indicating the importance of the heat transfer in engineering sciences. It is clear that the engineer and the scientist must have a thorough knowledge of the science of heat transfer to be able to quantitatively analyze problems involving transfer of heat. So basically, as I told you yesterday also, it's a very important subject. Okay, to know about the heat transfer, or how to calculate the heat transfer, or to design the equipment based on heat transfer. Okay, now what are the various mechanisms of the heat transfer? The various mechanisms you must know is, the first one is the conduction, second is convection, and the third is radiation. So let us first of all talk about heat conduction. It is the mode of heat transfer accompanied via two mechanisms. Now how heat conduction takes place? It is just because of the temperature difference it is taking place, or between the uh, if that there is some temperature gradient which is occurring at one end to the with respect to the other end, it is taking place, the heat transfer is taking place. But now we are talking about how and what are the mechanisms of this heat transfer. The first one is the bimolecular interaction, whereby the energy exchange takes place by kinetic motion of direct impact of molecules. Molecules at relatively higher energy level or temperature impart energy to the adjacent molecules at lower energy levels. This type of energy transfer always exists so long there is a temperature gradient in the system comprising molecules of a liquid or a gas. So basically it simply means, suppose there are you are if you are considering a particular material of adjust consisting of adjacent molecules, and if the molecule on the left side is at a higher energy level, whereas the molecule just right to it is at a lower energy level, so the energy will be transferred from the left molecule to the adjacent molecule, and then to the next molecule, and then to the next, and so on. This is how the heat transfer or the means energy transfer will take place because of the molecular interaction. The second is by the drift of the electrons, as in the case of the metallic solids. Okay, the previous example is also valid in case of liquids actually. Okay, now we are talking about the metallic solids. The metallic alloys have different concentration of the free electrons, and their ability to conduct heat is directly proportional to the concentration of the free electrons in them. The free electrons concentration of I think there is some mistake. I will see it. Hence, materials that are good conductors, like pure metals like copper, silver, etc., are good conductors of heat too. Pure conduction is found only in solids. So this is very, very important that conduction is found in solids. So you should remember that the solids will have more conducive to conduction. So these are two phenomena. Now let us talk about convection. Uh, Rather, I will make some diagram here also. For example, if this is one molecule, this is next, and so on. Okay, so if the temperature of this molecule is 30 degrees Celsius and the temperature of this molecule is say 20 degrees Celsius, so automatically the heat will flow from one molecule to the adjacent, and so on. The heat will be transferred across to the other molecules which are adjacent to the uh, other molecules. Now let us talk about convection. Now convection is possible only in the presence of a fluid medium. So remember it is possible only case of fluid medium. When a fluid flows inside a duct or over a solid body, and the temperature of the fluid and the solid surfaces are different, heat transfer between the fluid and the solid surface will take place. So when we will study about convection part, convection laws, so you will see how this convection takes place. So basically, convection takes place between a solid surface and a fluid actually. So solid surface could be wall also, wall of the home also, and a fluid could be the air, surrounding air. So that mode of heat transfer, when the air comes in contact with the solid wall and takes the heat from the wall, that is actually convection. This is due to the motion of the fluid relative to the surface. This type of heat transfer is called convection. The transport of heat here is inseparably linked with the movement of the fluid itself. So basically, if I say this is a solid surface here, and suppose some air is flowing over it, so that means the heat transfer will take place from this solid surface to the air here, and this mode of heat transfer is actually known as convection. Now next thing, if the fluid motion is set up by the buoyancy effects resulting from the density variation caused by the temperature difference in the fluid, the heat transfer is said to be free or natural convection. So it means buoyancy. You understand buoyancy. For example, if you talk about uh, means when the density variation exists between a fluid, because of that the motion of the fluid takes place automatically. So if you have a heated surface like here, if I will show you here. Suppose this is a heated surface at say 100 degrees Celsius, and the air over it is stagnant. Okay, we have a stagnant air over it, and when it comes in contact with this solid surface, what will happen? The temperature of this stagnant air which is in contact with the solid surface will increase, so this air will go up and the cold air will come down. So a sort of convection currents are set up, and the cold air comes down and the hot air goes up. and this is how the heat transfer will take place. And this phenomena is actually known as free or the natural convection. Then there can be forced convection also. For example, in case of radiators, car radiators, or you're in window AC, if you have a heat exchanger, like you talk about a radiator, in radiator what is happening, car radiator, the water flows down, the water is flowing down, this is the hot water, okay, it is going down, and you have a fan here, the fan is drying air over this radiator, and it sucks the hot air over it. So this is how the heat transfer takes place. So this is once again because of convection only, but now in this case we it is the forced convection, because we are forcing the air to flow over the radiator or the heat exchanger. So this is known as forced convection, because we are using some external agency here, okay, like blower or fan. An energy transfer between the solid surface and the fluid at the surface can take place only by conduction. The heat transfer by convection is always accompanied by conduction. So this is also very important line, important information. For example, what is the meaning here? See, if this is a solid surface here, okay, if this is a solid surface, and let us say the top here, the temperature is say 100 degrees Celsius, and there is air which is in contact with this solid surface, okay, this air is actually stagnant, because this air is stagnant. So the heat transfer will which will take place from this solid surface to this stagnant air, this heat transfer, that heat transfer will be because of conduction, it is q conduction, okay, because the uh, uh, air molecules are in stagnant condition here, and basically this layer which is stagnant and which is sticking to this solid surface, this layer which is sticking to the solid surface is having a velocity which is equal to 0, and this condition of sticking a stagnant layer of air over the solid surface is known as no slip condition. No slip condition, it means this layer which is in contact with the solid surface has zero velocity. Now let us talk about radiation. If two bodies at different temperature are placed in evacuated adiabatic enclosure, they are not in contact through a solid or fluid medium, the temperature of two bodies will tend to become equal. So suppose this is the adiabatic enclosure, one body is here, another body is here, and its temperature is T1, its temperature is T4. After a period of time when the heat exchange takes place between these two bodies, okay, and evacuated means there is vacuum actually, okay, there is vacuum. So when the vacuum is existing, after a certain period of time, you will see that both the bodies are at the same temperature, that T1 is equal to T2 after the heat transfer takes place because of the radiation. The mode of the heat transfer by which this equilibrium is achieved is called thermal radiation, because I would like to tell you, in case of conduction and convection, we require a material medium. For example, if I talk about conduction, I said I need some solid surface, I need a solid body, okay. When I talk about convection, I said I need a solid surface and a fluid, okay, this is what is required to me. But when I am talking about radiation, I am saying that I don't require any material medium. I This radiation can happen in case of vacuum also. So radiation is an electromagnetic wave phenomena, and no medium is required for its propagation. In fact, the energy transfer by radiation is maximum when the two bodies exchanging energy are separated by a perfect vacuum. So this is very important. So that means you can understand that maximum energy transfer will take place when there is vacuum, because if there is some material medium in between, then some part of the energy which is being transferred from the one body to the another will be absorbed by the intervening medium actually. So in that particular case, the heat transfer rate will reduce, or the heat transfer will reduce. So thermal radiation depends only on the temperature and on the optical properties of the emitter. This we will study later on. There are some properties like absorptivity, transmissivity, epsilon means emissivity. Okay, so this you must have studied earlier also. Then rho stands for reflectivity. Okay, these are some properties of the surface. Now, what could be the other cases? Now we have talked about three ways of heat transfer. Three ways of heat transfer is: one is conduction, other is convection, and other is radiation. So three modes of heat transfer we have studied. But how these can occur actually? Now there can be different cases of the heat transfer. What could be those different cases? See, one could be, it could be a steady or unsteady heat transfer. In some cases, when the heat transfer rate is constant with time from a surface, then it will be steady. If it is not constant, then it is unsteady. A steady process is one which is not dependent upon time, that is, the rate of the heat transfer does not vary with time. You know about it. In a steady process, there can be no change in internal energy of the system because the rate of energy influx is equal to the rate of energy efflux. That is the heat transfer from a hot to a cold surface in a heat exchanger. If you are considering a steady case, in that particular case, there is one fluid which is entering from in a heat exchanger from left side, it is going out from the right hand side, and there is heat transfer between the two fluids actually. See, in heat exchanger there are always two fluids actually. Okay, so that is a sort of steady state heat transfer example. Now there can be certain cases where the heat transfer is unsteady. For example, unsteady could be like soaking of ingots or heat treatment of metal casting. You know, when the metals are heated during the heat treatment, the initial temperature of the material, okay, could be say um, 200 723 degrees Celsius. So it's quite high temperature. And then this material is losing the heat, or the steel is losing the heat to the surroundings. So over a period of time, the temperature will reduce to ambient actually. So this is a sort of unsteady heat transfer. So this is more complex. The analysis of unsteady heat transfer is more complex in nature. It becomes more difficult to analyze it. But when we talk about the steady processes, it's quite easy. We can derive the equations for that also. There could be periodic or quasi-static heat transfer also. Okay. For example, in case of cylinder walls of an IC engine, the basic processes of heat conduction, convection, and radiation are often combined both in nature and in engineering applications. Okay, so I told you about conduction, convection, and radiation, but in most of the cases, these three modes of heat transfer takes place simultaneously. For example, if we talk about the boiler tubes, they receive the heat from the products of the fuel combustion by all three modes of the heat transfer. So all three modes of heat transfer are taking place when the heat is being transferred. Therefore, it is not actually possible to isolate entirely one mode of interaction with the other two other modes. So this was, you can say, a basic introduction of the heat transfer. We have talked about, I will once again go through it. First, we talked about the thermodynamic part, heat, work, and energy. Then we talked about the temperature. Then we talked about the difference between heat transfer and thermodynamics. Okay. Then we discussed about certain applications of the heat transfer in engineering. Then I have discussed about the mechanisms of the heat transfer, conduction, convection, and radiation. Then I discussed about the various cases of the heat transfer. Okay, could be steady, unsteady, could be uh, like periodic or quasi-static, and so on. Okay, so this is what we talked about. Now this is the next topic, and this is Fourier's law of heat conduction. So this you must have studied in your 11th or 12th class also. Now let us see it here. What is Fourier's law of heat conduction? So Fourier's law of heat conduction. Now we are talking about the various laws which govern the heat conduction, convection, and radiation. As per Fourier's law, heat transfer rate per unit area is proportional to temperature gradient. So this area is normal area. So what I am saying is, for example, if I am considering this surface here, okay, this is, you can say, it's a wall here, and it's this surface is at a temperature, let us say 50 degrees Celsius, and this surface, this whole surface actually, and its opposite surface, which you are not able to see here, uh, okay, this surface, the blue surface is at 50 degrees Celsius, whereas this red surface, let us say, is at 30 degrees Celsius, and this has a thickness of, let us say, L, or I can also call it as delta x, or delta x, dx, or delta x. So I am talking about, uh, I am saying that area, normal area. So that means I am talking about this area. I am talking about this area, or I can say, if in simple words, this is the area. This is the area normal to the surface actually. So I am talking about this area. Okay. So if this is the length and this is the height, then this area is actually L into H. So heat transfer actually takes place in a direction normal to the surface. So heat is flowing in this direction. So area is L into H. Okay. So here I can say Q by A. So what is this? This is Q dot by A. I told you what is this? This is heat flux. This is heat flux. So heat flux is proportional to temperature gradient, because the surface here is at a higher temperature T1, whereas the temperature here is T2. So the heat transfer is taking place in this direction, and this is actually, you can say, delta x. So I can say Q dot per unit area is equal to minus k dt by dx. When I remove this proportionality sign, I introduce a constant here, which is represented here by k, and this k is called thermal conductivity of the material. What is this k? This k is thermal conductivity of the material, and dt by dx is the temperature gradient in the solid body, and this area is the area which is normal to the surface through which the heat transfer is taking place. So heat is flowing in this direction, and the area is this one, this area I am talking about. Okay. So this area is A. So basically I can say that Q dot is equal to minus Ka dt by dx. Now this quantity can be written as Q dot with double prime. So this is heat flux. What is this negative sign? Why we are putting a negative sign here? Because if I want to calculate the value of Q dot, it comes out to be minus Ka dt by dx. So when I will integrate this equation, when I will integrate dt, or this equation, it will be final temperature minus initial temperature, and the heat transfer always flows from high to low, and T1 is the higher temperature, whereas T2 is the lower temperature. This is lower and this is higher. So the formula may come out to be minus Ka uh, T2 minus T1 divided by some length L. Okay, which we will get when we are integrating dx. So it will come out to be L. So it means, because this is lower and this is higher, so we need to put a negative sign here, because heat always flows from high temperature to low temperature. So it is written here, negative sign is introduced because heat flow always occurs in the direction of decreasing temperature, and hence dt by dx is equal to negative. Therefore, to make it positive, we have introduced a negative sign so that the final value of the heat transfer comes out to be positive. So I hope this is clear. This is Fourier's law of heat conduction. So normally, if you are asked to write the expression for the Fourier's law of heat conduction, you can always write it as Q is equal to minus K into A dt by dn. See, why dt by dn? I am saying that this is the direction which is normal to the direction of the heat flow. So I am saying it is in the normal direction rather than writing x. No, I am writing dt by dn. For example, if it is a curved surface, so the heat transfer will take place. If I am talking about, it will take place normal here. The normal direction will change here. It will be taking place in this direction. So this is actually normal. Here it is normal. Okay, and this is q. So but mostly the cases which we will be discussing, there we will be talking only about either rectangular coordinates, that is uh, Cartesian system of coordinates. It could be cylindrical system of the coordinates. For example, if we are analyzing a cylinder, then we will be going for the cylindrical coordinates, or it could be spherical coordinates if we are talking about the heat transfer in case of a spherical body or a sphere. Okay, so this is the equation of the conduction. This is Fourier's conduction equation. Q dot is equal to minus Ka dt by dn. Now I am talking about a plane wall case. So you can see it here. This is a plane wall, case of a plane wall. So now I am going to calculate the conduction heat transfer in a plane wall. So you can see it here. I am making certain assumptions. What are those assumptions? First of all, I am saying one dimensional heat transfer. Second, I am saying it is a steady state. Third, I am saying that the thermal conductivity is constant. What is thermal conductivity? Q is equal to minus Ka dt by dx, and this K is thermal conductivity. And if you will calculate the value of unit of this thermal conductivity, it will come out to be watt per meter Kelvin. This you can easily find out from the equation that K is equal to Q into dx divided by A into dt. So the value of Q dot is watt meter per meter square and Kelvin. So you can see it comes out to be watt per meter Kelvin. Okay. So assumptions is one dimensional heat transfer, steady state. Steady state, you understand the properties are not varying with respect to time. Thermal conductivity is constant. That means K is equal to constant. So normally what happens, the material which we are using, they have different values of thermal conductivities in different directions. Suppose if I take a Cartesian system of coordinates x, y, and z, then I can always say that the thermal conductivity in x direction is kx, in y direction it is ky, and in z direction it is kz. Okay, so but here what I am saying is thermal conductivity is constant, and moreover it is a one dimensional case, so we should not worry whether it is kx, ky, or kz actually. And we have isothermal surfaces. Isothermal surface means if I am considering a plain wall or a slab, so the left face is at temperature T1 and the right face is at temperature T2. And because this temperature T1 is greater than temperature T2, so heat transfer will flow in a direction which is perpendicular to the wall surface. Okay, so this is the direction of the heat transfer. And one more thing we have shown here, the axis also. I am saying that the left face of the wall, the left face of the wall is at a distance x1, whereas the right face of the wall is at a distance x2. You can see it here. This is at a distance x2. So the thickness of the wall is actually x2 minus x1. So this is at a distance x2 and this is at a distance x1. So that the thickness of the wall is x2 minus x1, and I have assumed that x2 minus x1 is equal to L, which is basically depicting the thickness of the wall. What is L? It is the thickness of the wall. So now we can apply the Fourier's law. Once again, you can see it here. I have this wall here. This is at a distance, left face is at a distance x1, this is at a distance x2. The temperature here is T1, temperature here is T2, and let us say that the thermal conductivity of this surface is given by K. Okay, and this x2 minus x1 comes out to be, let us say, L. So as per Fourier's law, I can write this equation. Now, because I am considering the x direction heat transfer or the one dimensional heat transfer, I am using here dx because the heat transfer is taking place uh, in this direction. This is the direction of the heat flow. This is q dot which is taking place, and I am also saying that T1 is greater than T2. So what I can do is I can take this dx on this side, a can be taken on this side, and I get q dx is equal to minus ka a dt, and then I can integrate this equation between x1 to x2. So q dx, and here this side I have minus ka dt, so I can integrate between t1 and t2. So it's a simple integration. I will integrate it and I get on the left hand side q x2 minus x1, and on the right hand side it is minus ka t2 minus t1. And this x2 minus x1 I told you is L, which is the thickness of the wall, and it is Ka T1 minus T2, and this minus sign has have been absorbed here within the brackets actually. So finally I get this particular expression, Q is equal to Ka T1 minus T2 divided by L. So this is the equation of heat transfer in case of a wall. Now I can write it in a different fashion here. I can write it as Q is equal to, once again it is the same equation, Ka T1 minus T2 divided by L. So I have given the units here. I have already told you area in meter square, length or thickness in meter, temperature in degree Celsius or Kelvin. Okay, it will be same, because if I am taking T2 minus T1, whether I use Kelvin or whether I use degree Celsius, and it's a difference, so it will not be, it will be immaterial. This is the value of unit of thermal conductivity K. K unit is watt per meter Kelvin. Watt per meter Kelvin. And finally, just you see from this particular equation, I can always write this equation as T1 minus T2 divided by L over Ka. So now it becomes T1 minus T2 divided by R thermal. R thermal. R thermal means resistance. Why I am saying it is resistance, I will let you know if it is given further. Okay, so let us see it once again here. So what I am considering, if I consider an electrical system, and the resistance, this is the electrical resistance and this is the current which is flowing through it, and the potential difference which we have applied here is V. Okay, so you know from the Ohm's law, V is equal to I R. I can also say that current is equal to V by R. Now what is this V? V is electrical potential difference divided by electrical resistance. Okay, electrical resistance. See, in a similar way, when I have a thermal system, what I can say is this is the resistance, this is now the R thermal. Okay, and what is flowing here from the one end of the wall to the other end of the wall, it is the heat which is flowing. Heat transfer rate is taking place, and I can say on the left end the temperature is T1, and on the right end the temperature is T2. So I can, by analogy, I can always use this particular equation of the electrical circuit to heat transfer circuit also. So I can say, by analogy, I can say that Q dot is equal to In electrical circuits, we were using here in numerator, we were using electrical potential difference. Here we will say thermal potential difference. So delta T thermal divided by R thermal or thermal resistance. So you just compare this equation with this particular equation. Okay, these two equations you compare. So this is the value of delta T thermal. This is thermal potential difference. This is thermal potential difference. And here we have the thermal resistance. And what is the value of this thermal resistance? It is actually L by Ka. So L by Ka is the thermal resistance, and its unit will be Kelvin per watt. And if I take Ka by L, Ka by L, it will be conductance. It will be conductance, and its unit would be watt per Kelvin. Because you can understand, once I am talking about resistance and other time I am talking about conductance, both are reciprocal of each other. So if the unit of thermal resistance is Kelvin per watt, for conductance it would be watt per Kelvin. And if I am saying K as the conductivity, then 1 by K will be resistivity, and so on. So this is what I wanted to teach you today. Just wait for a minute. I will take your attendance and then you can leave. If you have any questions, you can ask also.